right now. Okay, let's go ahead and get started. So here's the sign-in sheet. I just gave you back homework 2. The TA's working on grading homework 3, and obviously working on grading homework 4 since you all just turned that in. I'm trying to get it back to you as soon as we can. I just gave you back homework 2, and as of right now, all 4 homework solutions should be posted online. So you should have everything there. Did it show up as invisible? Okay, good. All right. What we're going to do today is I'm going to talk about the exam. We're going to talk about just the format and what's on it, and then up to you to ask whatever you want. And we can talk about homeworks, we can talk about content, we can talk about whatever you want. Just hopefully you came prepared, ready to ask questions. Okay? So, first off, the exam's going to be closed book, closed notes. As for what you're allowed on the exam, you're allowed a calculator, you're allowed a formula sheet. You can put whatever you want on the formula sheet. Just know worked out examples. You can put procedures, you can put things like that. One thing not to put on your formula sheet are like the rebar tables. Don't worry about that. I'll give you that. I don't need you wasting space on your formula sheet, putting anything like that. If there is tabular information that you need, you will have it. And by tabular information, I just mean like tabular data of your rebars and things, rebar and things like that. As for shear and moment aids and whatnot, what I'll say is this. If there's aids that are esoteric, that are out there that you need for the exam, I will give them to you, okay? What I would not do is not know how to use WL squared over 8. You know, I mean, the basic ones, I mean, I may or may not give them to you, but whether or not I give them to you or not, if you can't do that, that's, you probably got bigger problems than whether or not I put the 8 on the exam or not. Now, I'm going to give you all the same deal I gave in steel design. If you show up, if everybody is here, okay, and notice how, like right now, I've got like 4 homeworks in my hand, so you might want to get the word out to your friends and whatnot. If everybody is here, we will start 5 minutes early, okay? And we'll go till 10:55, okay? But if everybody's not here early, we got to start at 10, okay? So get the word out. I'll provide scratch paper, I'll provide, you know, all that stuff. Just bring pencils, a calculator, and your formula sheet. Sound good? Area of coverage on the exam is lecture notes 1 through 8 and homeworks 1 through 4. You have all those solutions, all those notes are posted on Blackboard. As for what's on the exam, make sure you can generally describe like what it is we're after, you know, designing structures safely and economically. Tell me what the difference is between ASD and LRFD. Make sure you can do that. Loads, gravity loads, big part. Make sure that you can identify the tributary area of elements in a frame structure. I want you to perform basic load takedown. Be able to perform basic load takedowns for gravity loads. Be able to perform live load reduction when necessary, and be able to factor the loads according to LRFD load combos. I'm more concerned with gravity loads in this class. I mean, maybe describe what's going on with wind, what's going on with seismic, but it's not like steel design where in there I expect you to have a more in-depth understanding of wind and seismic. And here, I want you to have a more in-depth understanding of your gravity loads. So, dead and live, tributary area, things like that. As for the big topics on the exam are making sure that you can describe just the basic properties of concrete, that you know what the stress strain curve looks like, you know that it's a non-linear material, and so on and so forth. But the big part of this exam is flexural analysis and design. So, make sure that you can analyze beams that behave elastically up until their cracking moment. So that's stage 1 behavior. So stage 2 would be after they crack. So that's the transformed section. Remember turning your steel into an effective lump of concrete and then computing your crack moment of inertia and so on and so forth. Make sure you can employ the Whitney stress block approach. And so when I say Whitney stress block approach, I mean the 0.85 FC prime block that's A deep and so on and so forth. A equals beta 1 times C, all that. Make sure you can do that to compute MN and PMN. We're looking at rectangular cross sections for this exam, no T-beams, nothing like that. Make sure you can verify ACI requirements for the minimum area of steel and the minimum steel strength, or the steel strength. Also, I want you to be able to design beams with an unknown cross section, design beams with a known cross-section, and design slabs. And as for some relevant formulas, so here's our loads. So the unit weight of steel, 490 pounds per cubic foot. Unit weight of reinforced concrete, unless otherwise told, 150 pounds per cubic feet. So this is a common value unless you're told otherwise. Live load reduction, here's your formula for live load reduction, pretty straightforward. Live load element factors, 2 for beams, 4 for columns. Live load reduction doesn't apply whenever your influence area is less than or equal to 400 square feet. It does not apply when your original live load is greater than 100 pounds per square foot in most cases, and for us that's going to be all the time. Remember, you can't reduce to more than 50% for a beam and 40% for a column. Load combos, here are the ASC 7 load combos. Really the two that we're primarily after are 1.4 dead and 1.2 dead plus 1.6 live. 1.4 dead usually only governs when you have a really high dead to live load ratio, like 90 kips of dead load and like 2 kips of live load. That's when the first one would govern. Otherwise, the second one's going to govern all the time. Material properties. So what do we got for concrete? Well, we know that the unit weight of concrete, the compressive strength, the modulus of elasticity. The modulus of elasticity can be computed as 57,000 square root of FC prime for normal weight concrete, and for pretty much any other concrete, 33 times WC raised to the 1.5 times square root of FC prime. Lambda, here are the simple values. Lambda is 1 for normal weight concrete, 0.75 for lightweight concrete. For sand, lightweight concrete, it can be in the middle, 0.85. That's just me distilling what's in the ACI tables. F sub r, your modulus of rupture, 7.5 lambda square root of FC prime. What's the deal with the square root of FC prime? We put in PSI, we get out PSI. Okay, so one real big piece of advice I will give you on this exam is make sure that you are comfortable and cognizant of your units. Units is a big deal on this exam. Young's modulus for steel, 29,000 KSI. The strain of the steel at yielding is Fy over ES, and then our modular ratio is the ratio of those two Young's moduli. Modulus ratio, or modulus of elasticity for steel over the modulus of elasticity of concrete. Flexural analysis. So the cracking moment is just FRIG over YT. And so the cracking moment will tell you whether or not you're in stage 1 behavior or stage 2 behavior. Either the moment is less than that and it's uncorrect, or it's more than that, it's cracked. As for everything else, stage 3, our maximum capacity. What I have here on this slide is I put a diagram on the bottom that has pretty much all of the fundamental notation that we've been using so far. So the beam is B wide, it's H tall, but we don't really care about H when we're looking at flexural analysis. We care about D, from the top of the beam to the steel layer. Okay. Now the neutral axis, where there is zero strain, that depth is C. The depth of the stress block is A. Remember, A equals beta 1 times C, so there's a difference. The stress block is always 0.85 FC prime. Doesn't matter if it's a T-beam, triangular beam, circular beam, looks like Mickey Mouse, it doesn't matter. It's always 0.85 FC prime Y. The compressive force is 0.85 FC prime times A times B for a rectangular beam. The tensile force is ASFY, so set those two equal to one another, and that tells us what A is. So ASFY over 0.85 FC prime B. That A also equals beta 1 times C, so that's just me consolidating that. And remember our nominal moment capacity, force times moment arm, F times Z, so the force is either C or T, doesn't matter, but I'm being lazy, so we use T. That's obvious, that's what you always use in concrete design. And then your moment arm, D minus A over 2. That's the center of this and the center of that, so that's that distance. Strain in the steel, this strain right here is 0.003, D minus C over C, just using similar triangles. And then the limiting strain is the yield strain plus 0.003. So if this value is larger than that, that means we're good. It also means that phi is 0.9. If not, that means you have to compute phi. What else? Beta 1. So remember, beta 1 is the measure sort of ductility. It sort of measures ductility in your section. If your FC prime is less than or equal to 4,000 PSI, beta 1 is always 0.85, and then it drops down from there. I put the formula there for you to compute that. If it's greater than 8,000 PSI, beta 1 is 0.65, and everywhere in between it's just a linear fit. Phi, so for beams have to be tension controlled, so you know, we assume that B is 0.9, but it's something we always have to go back and check. Like when it's all said and done, whether we're analyzing a beam or designing a beam, we pretty much have to ensure that phi is 0.9. In other words, we have to ensure that the strain is larger than the strain at yield plus 0.003. And that's for elements that are undergoing primarily bending. Later on, when we look at columns, that isn't the case because there is no tensile strain in a column. You're just pushing on it. But if you have a strain value in between, that's how you would compute it. Just that linear fit equation that you see there. Last, I think this is the last thing. No, I don't. Okay, so rho values for design. Remember, we have one of the most important tools for design is the reinforcement ratio. Remember, a reinforcement ratio by definition is AS over BD. So it's basically how much steel you have versus how much concrete you have. So you can kind of think of it as like a percentage. You know, so if your beam is 100 square inches and rho is 0.02, so 2 square inches of that needs to be steel. That's an oversimplification, but close enough for government work. When you have an unknown cross-section, you kind of have to guess a rho value, and so there's a couple ways of doing that. One of them is to just guess one, and so that 0.18 FC prime over Fy is just that. It's just kind of guessing something. The other is to maybe be a bit more scientific about it, maybe compute a rho value based on a given strain. Like, I want to design this beam so that the strain in the steel is 0.01. So what rho value do I need? That's another way that you can compute that. Now that's for if you have an unknown cross-section. You don't have a clue what the beam looks like. You got to have a rho value to start with. What if you do know what the beam looks like? What if you are dealing with a known cross-section design, which is also a slab design? Keep that in mind. If I'm dealing with a known cross-section, well, I can just solve for it. So it's just doing a little bit of algebra and solving for rhos. That's why I'm using like rho design versus rho required. Rho required is something I can solve for. Rho design is just a value I'm guessing to come up with some dimensions to work with. Lastly, we have 2 ACI requirements that we have to meet. Our strain has to be greater than or equal to the limiting strain, and our minimum steel. Our steel area has to be bigger than that, which is BD over Fy times the square root, or times the maximum of either 200 or the 3 times the square root of FC prime. Bless you. Lastly, we got the slab reinforcement. What I did here on this slide is I've got on the left, remember we have our AS required, which is our main steel, AT required, which is our temperature steel. And then over here, we have the maximum spacings, either for the main steel or the temperature steel. Excuse me. That's the exam. So, like the steel design exam, I will go ahead and tell you it's going to be one set of conceptual questions and then 3 problems. It'll be the same thing. I will tell you 2 other things. I am still going to use my rule of 3, although I think the steel design folks wish I'd use like a rule of 4 or something like that. Maybe I'll look at that. But I will say one final thing before I turn it over to you. Some of the examples that we did in class and some of the homework problems were kind of long. They're really big, right? So I know that, okay? And I'm not going to make you do 4 full-blown design problems in an hour, okay? So I'm not doing that, okay? I might have you do pieces of that problem or do a small snippet or something like that. But my intent is to not design a test that is impossible to do in an hour. I don't like that, okay? That's my intent. I've always used a rule, whether it's 3 or 4 or something, you know. That's my goal, is to ensure that I'm not designing an exam that's impossible to do. Am I going to have curveballs on the exam? Yeah, probably I will. That's just fun on my part. You're like, yeah, it's not very fun for us. But if you understand the material, if you understand the process, I think you're going to be fine. I'm going to shut up now. Floor is yours.
So there was on homework 2 that you just passed back.
Yes.
The triangle part for the last problem.
Yes.
Is anything going to be left out of the test?
Is anything like the triangular beam going to be on the exam? I think it's a safe bet to say no, but don't take that as, oh, we aren't going to have to do any algebra ever. Don't take that as we're not going to be challenged. But that particular problem, no. Because the only other section that I can give you that let me say two things before I say it. First thing is, T-beams are kind of that. It's me saying, okay, what if the beam wasn't rectangular, right? That's what a T-beam is. And that's a whole can of worms in and of itself, as you realize. As a result, we're not putting that on the first exam. The only other section that I could give you that is a realistic section that you would experience in real life is a column that's circular, right? And so you have, let's say you have 1, 2, 3, 4, 5, 6 pieces of reinforcement. And so here's your compression block, and here's your tension, right? Well, that just becomes a geometry problem, because this isn't a half circle. It's like a circular sector, right? And so it's you finding the area of that, and then it stops becoming concrete design and starts becoming geometry. And this isn't a geometry class. So that's not what I'm going to do to you. I'm not trying to do that. I'm not trying to trip you up on stuff that isn't concrete design. I'm not trying to do that. That's not a point. There's no point to that. There is a reason why so far, and I know, we had, like the triangular load and whatnot, but by and large, most of the structural analysis that we've done in here has been pretty simple. Because I'm not trying to give you a beam that has a hinge and has this and that and, this distributed load and then a hinge here and then that support and that support. We're not doing that in here because we already did that last semester. That doesn't mean you don't need to understand it. I'm just not making it super, super difficult, okay? We did have a truss on the steel exam, but it was pretty simple, It wasn't this super monstrosity, so I'm not trying to do that to you. I went a little bit off on a tangent there. That kind of answer your question?
Yeah.
Right. Well, there's got to be more. There's got to be more questions.
I got one.
Yes, sir.
So on the nominal moment equation, and we use the area of the steel, do we include the temperature still?
No.
Okay.
No. Because here's the reason why, okay? Here's the slab, okay? Here's the slab. Say slab bends this way. One-way slab, right? So the steel that I care about when it comes to bending is the steel that's going this way. Bending it, right? That's the main steel. The main steel goes in the direction of bending. The temperature steel goes this way. When I bend it, it's just going along for the ride. It's not resisting the load at all. Like I'm not having to force that to bend. It's just going along. So when I compute the MN capacity, I care about the steel that's actually resisting the load. So when I'm looking at a one-way slab and I compute MN, do I care about AT? No, I don't. Absolutely not. Did that make sense? I mean, imagine taking this, right? Okay, imagine this notebook, okay? And imagine me taking like some balsa wood strips and gluing them this way and gluing them this way. When I fold the notebook this way, I'm going to crack the ones going this way, but not the ones this way. They don't care. Does that make sense? They just go along for the ride. They don't resist the load at all. Does that make sense, everybody else? And so when you compute your AS versus AS min calcs, you don't care about AT at all. It's just the area of steel. It's all about the main reinforcement. That AS min calc is intended to ensure that the beam, or the slab in this case, does not prematurely fail. Well, that temperature steel isn't doing that. It's not resisting that load at all. It's just there to prevent cracking in the other direction due to temperature changes. So no, that's not a problem. Did that answer your question?
Yes.
Everybody else good with that? All right. There's got to be more than that. We got plenty of time. Close to a half an hour. Yes?
Does the wording of the problem, I'm kind of relating to like this homework problem 5, does the wording of the problem determine whether you use C or T as your force in the nominal moment equation?
Doesn't matter which one you use.
Okay.
It really doesn't matter. right? Okay, your MN expression could be, you could do this. Or you could do this. If you don't believe me, take problem 4 on that homework assignment. Do both of them. You'll get the same answer. The reason you're going to get the same answer is because this and this equal one another. That's how you solved for A to begin with, by recognizing that these two are equal. Now, why is this term the same? Because here's your stress profile. Here's the tensile force, there's the compressive force, right? Regardless of which force you use, there's where that force acts, right? There's the center. This distance, Z, is D minus A over 2. It does not matter whether you look at this force or look at that force, the distance between them is the same, hence why that distance is the same. It's a force times a moment arm. As for the force, you can use either one. So the problem isn't going to state that you have to use one or you have to use another. It doesn't matter. All right? Why have we written our formula this way as opposed to this way? Because I'm lazy. I don't want to multiply 4 things together. I'd rather just multiply 2 things together. I'm lazy. But again, go to problem 4. Try this out. You get the same answer. Guaranteed. Because problem 4 on homework 2 was just, here's a beam, tell me what MN is, right? So, do it. And you'll see you get the same answer.
I got marked out for some reason I was asking.
What do you mean? What'd you get marked off for?
Just using like the T or the C instead of T. I know that one had like the weird wording. It was like tensile reinforcement reaches the yield stress.
Let's look at that problem later, okay? Look, come see me later, and if your algebra is right, you might have gotten points taken off that you didn't deserve.
Okay.
But let's look at it later, okay?
I know that one had a little bit weird wording, so I didn't know if that mattered or not.
No, that shouldn't have mattered. That shouldn't have mattered.
Okay.
We'll look at that later. Yeah, but that should not, if it was just that, you shouldn't have gotten taken, or points taken off for that. Oh, there's got to be more than that. Yes, sir.
So you said that you, about the WL squared over 8 thing,
Yeah.
and for that's distributed loads, will you be giving us the formulas for like a point load, or a triangular load, or a cantilever?
If you need it.
Okay.
But again, I don't want this exam, let me say 2 things. And I know these might not seem to correspond, but just bear with me. I don't want this exam to be a test of structural analysis, okay? But that being said, if there is structural analysis, I want you to be able to do it correctly, okay? Now I'm going to guide our discussion a little bit because I want to talk about a homework problem that you all just turned in, and that's homework 4. Specifically problem 2, okay? I want to talk about this real quick. All right, here was the problem. How many of you all felt a little uneasy about this problem? It's okay if you did. All right. Let me show you something. Okay. So this is W sub L, and I believe this was 3 kips per foot. This was W sub D is 1 kip per foot. And there was a self-weight, which you didn't know, but you could determine, right? Because what were the dimensions of the beam? B was something, H was something.
15 and 38.
15 inches, 38 inches. And then, hold on, we had a unit weight of concrete, right? How long was the beam, by the way?
20 feet.
20 feet. many of you were like, what the heck's going on? It's okay. All right, how many of you tried to do this? And then, I don't know, something like maybe over 2 or 8 or something. How many of you did that? Okay. Take your hand. Not correct. No. All right. I'm going to walk you through this. Is that fair? That's fair? Is that fair? Tell you what, let's do this. This is 0.150 kips per cubic feet, so let's replace this. Somebody give me an answer on this. Maybe I'll do some work. Which, while you're punching this out, I'm sure some of you are curious. I did my very best. I wasn't able to get your steel exam graded by today, so I don't have that. So I thought I would just mention that. I tried, but it just didn't happen this weekend. So I thought I'd just be honest. All right, what do we got here?
0.594.
Do I have a second on that?
Yep.
Okay. So, is that a fair statement? Okay. So, if I was looking at the dead load, whether I'm looking at the self-weight of the beam or just the dead load in itself, I'm looking at this situation. Is that a fair statement? Where is the maximum moment on that beam? At the support, right? And what is that maximum moment for a cantilevered beam? Is it WL squared over 8? No. It's WL squared over 2. And remember, how am I getting that? WL, that distance is L over 2. What's the moment from here? WL times L over 2, right? So what I can say is that the dead load moment is that. Fair statement? So, what are we getting for that? And so I'm running out of room on this board, so I'm going to put that over here. So we have a dead load moment of something.
318.8.
318.8. Do I have a second on that? 318.8 foot kips. Now, what does the dead load look like? Right? This is W. That dimension is L. Where is the maximum moment here? It's over here, isn't it? Same as it was here. How do I determine the moment right there. Well, how did I do it here? Force times moment arm, right? So, force times some moment arm. So what's the moment arm? From here,
1/3 of it.
L over 3. So ML is something times something, and that's L over 3. What about the force? What's the area of that triangle?
WL over 2.
1/2 W times L. Base times height. So 1/2 W times L. $400 times 3 is 1,200 over 6 is 200. Did I get that right?
Yeah.
What we got?
702.6.
Second?
Yeah.
Boom. I have here the solution to homework 4. If you go to problem 2, yeah, I got 72.5. Does that make sense? This is what I was saying on that slab problem. Remember that slab problem that we did? Here, I'm going to pull that up. No. Remember this? So this was the slab problem that we did. And remember how there were these two methods? How you could factor the load and then do WL squared over 8, but then you could calculate each moment independently and you get the same answer. The reason why you have to do this method is because they're not both simply supported beams with uniformly distributed loads. The load cases are different. Once the load cases are different, you had to treat dead and live loads separately. I swear, I saw some people on homework 4 that were still like, yeah, but I'm still going to try and do that. No. No. When you do that, what you do is you underestimate the amount of moment. Okay? You underestimate the amount of moment. All right? Let me show you. Watch this. Let's say you have a beam that's 40 foot long, okay? And it has a distributed load on it that's 3 kips per foot. What's M max? Well, it's WL squared over 8, which is what?
$600.
600. Now, instead of spreading the load out, let's say instead of doing that, let's say you lump the load all in the middle, okay? So 3 kips per foot over 40 feet is 120 kips, okay? But instead of spreading it out, I put it in the middle, okay? Now, if you go into that guide that I gave you all at the beginning of the semester, you will see that that's PL over 4, okay? Again, 40 feet, and this is 1,200, okay? What do you think's worse if I have a 40-foot beam? Lumping the load in the middle or spreading it out? Lumping the load in the middle, okay? If you go to problem 1, for instance, here's problem 1 that I gave you on the homework assignment. Okay, I've got dead load that's spread out, and I have live load that are 2 concentrated loads. Now, how many of you said, okay, this plus this is 70 divided by 27 is another distributed load, and then we'll do 1.2 times dead plus 1.6 times live. Anybody do that? Hope not. That's bad. That's not good. The live load is lumped in these 2 spots. If you take it and spread it out, that's an unconservative option. The worst case scenario is that those loads are lumped right there, okay? So you fictitiously spreading it out is wrong and is unsafe from a design standpoint. Does that make sense? Don't do that. Nope. All right. I've diverted enough. There's got to be more questions. There's got to be more questions. None at all?
Are you going to do some engineering 216 on us for the gross moment of inertia?
That's a good question. If I do, it won't be anything terrible.
2 sheets. You know.
No, honestly, probably, but it won't be anything terrible. My focus on this exam, though, is rectangular cross sections. That's my focus. I'm not even trying to curveball you there. And again, any rebar data I will give you. Do not worry about taking space up on a formula sheet with that. Any questions about the stuff on homework 2? Cracking moments, ACI requirements. On homework 3, design procedures. I mean, anything. Homework 1, gravity loads, live load reduction. This exam is going to be easy then, isn't it?
Is it?
I've learned a long time ago that there's a difference between what I think and what y'all think. I thought the steel design exam had enough time. I think I was alone in that thought. I think there'll be enough time on this exam. I'll try and go with maybe like a rule 4 on this. Not gonna go any more than that though. I'm trying. If I can do the exam in 15 minutes, y'all can do it in an hour. How's that? I think that's fair. Is it? You're laughing at me like,
That's just really fast. I mean, I'm impressed.
I do this stuff every day.
I was
It's not
gonna say,
impressive.
you do
It's-
this all the time.
Yeah, it's not, yeah. That, and I did kind of know what was on the exam before I started it, because I kind of made it, so. So-
We know what's on it. Can we do it? 60 minutes.
Give it to another profession, if they can do it. 15.
Well, I tell you, well, no, if I told you what was on the exam, then you'd only have 15 minutes to do it, because then you knew ahead of time. Maybe I'll give you like 20.
All right.
I mean, it was a good try. I give you that. See, maybe I'd use a different rule if we had one of those Men in Black neuralizers where I could just,
I get what you mean.
Can we give y'all 20 minutes before steel design as opposed to 10? Is that what y'all want? Any questions? Any more?
Are you gonna give us these like, as in like this format, or will you just like give us what we need? If that makes sense.
I'll give you what you need, and I promise, I'm gonna say two things. I'm not gonna lead you down the rabbit hole, okay? If you don't need that, I'm not giving it to you. You see what I mean?
Yeah.
I'll give you what you need, no more, no less. At the same time, if you truly only have an hour on the exam, I'm probably not going to try and say, okay, you need 100 billion design aids. You see what I mean? That's the only thing I think I can say with clarity at this point, and that I think is fair. If you need it, you'll have it. If not, you won't. Okay? I'll give you what you need. No more, no less. For the sole purpose of not trying to confuse you. Okay? I don't think it's, see, I'm not a fan of the exams where you're given this pages and pages of aids and you never use it. I'm also not a fan of exams where you've got this problem statement that's like a paragraph and then hidden in there is just write your name and you'll get full credit or something. I'm being facetious when I say that, but I'm going to give you what information you need and what data you need to complete the problem, and that's it. Because I'm not trying to confuse you. That doesn't mean I'm not going to challenge you, but I'm not going to lead you down, astray. I don't think that does you any good. In my opinion, if you're sitting there asking yourself, well, I don't understand what he wants, or I don't understand what to write to make him happy, as opposed to how do I do the problem, that's a bad test, in my opinion. Does that make sense? I'm not trying to confuse you that way. Again, doesn't mean I'm not going to challenge you, but I'm not trying to. If you're worried about trying to make me happy versus doing the problem, then I've done a bad job making the test. That answer your question? Oh, about the best answer I can give. Any other questions? Steel design folks, we meet at 11, you get an extra 5 minutes. The rest of you, I will see you on Wednesday. Dum dum dum.
Well, now I'm worried on Wednesday.
Yeah.